Welcome to the LMWC Learning Mathematics with Ms. Choekyi channel. Please do hit the like button and subscribe the channel.
Hello everyone. So today we are going to go through the examples of chapter number 1, real numbers, according to the NCERT textbook. So the first example we have in chapter number 1 is this example, and the question is, consider the numbers 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. So you are given this number, which is in the exponential form, 4 to the power n, and you are given that the power n, it belongs to a natural number. So when we say a natural numbers, we are talking about the counting numbers. So the counting numbers are 1, 2, 3, 4, and likewise. So if you replace the power n with the natural numbers, you're going to get a number, right? You're going to get some numbers. So let's just see up to few natural numbers. Let's first start with the first natural number, which is 1. So 4 to the power 1, I'm gonna get 4. Likewise, I'm gonna find out for few others. So 4 to the power 3, 64, 4 to the power 4, we have 256, and so on. Now the question says, if that is the case, like for any natural numbers, if you substitute it in the 4 to the power n, you're going to get some answers over here on the right hand side. Will you get a numbers which will end with the digit 0? So the last digit, will it get 0 at certain natural numbers? So since the counting numbers are like infinitely many, and we cannot be manually checking out for all the numbers, so to find the shortcut of that, we are going to use the first topic of the real number chapter, which was fundamental theorem of arithmetic. If you remember, we have gone through this. If you haven't, please go back to the previous video and check it out. So the fundamental theorem of arithmetic says that for any composite number, it can be expressed as a product of primes, right? Now if you look at the question, which is 4 to the power n, and if you concentrate on the number 4 is actually a composite number. It is the smallest composite number, and I can express this composite number as a product of primes. So I can express this 4 as 2 times 2, isn't it? Now, as per the questions, if you go back to the questions, you have to find a number which ends with 0. So since we know that it ends with a 0, means we are talking about something like this. If you look at the digit 10, the number 10 ends with the last digit is 0. So you need to check whether this 4 to the power n, will it get something like this. Since the last digit is 0, we have to understand that any number which ends with a 0 has to be multiple of the number 10 itself, right? So this 10 is actually a composite number, and this 10, again, I can write it in the form of product of primes, which means 2 times 5, I'm going to get 10. So what I understood here is that any number which has a factor 2 and 5 will definitely have a number ending with the digit 0. Now, if you go back to the question here, what we have understood is we have the factor 2, but we are missing the factor 5. We do not see a factor 5 over here. And thus, you will conclude that since 4n has only the factor 2 and not the factor 5, it cannot ends with the digit 0. So I hope you have understood these questions. Okay, so second example, we have find the LCM and HCF of 6 and 20 by the prime factorization method. So prime factorizations method, I need a vertical line and a horizontal line, and put the numbers in here. So 6 and 20. So we need to find a common factors of 6 and 20, and that is 2. So 2 times 3 is 6, 2 times 10 is 20. So since I cannot find a common factor of 3 and 10, so my HCF is the number 2 itself. So for the LCM, I have to proceed further from here. So I will just concentrate on the first number, 3. So 3 times 1 is 3. So 10, I just need to copy it down. And next, I will have to think of the digit 2. So 1, I'll just copy it down. So 2 times 5 is 10. Then it has to be 5. So 1 comma 5 ones are 5. Now the LCM of 6 and 20 are 2 times 3 is 6, 6 times 2 is 12, 12 times 5 is 60. So these are HCF and the LCM. Next example number 3, find the HCF of 96 and 404 by the prime factorization method, hence find their LCM. So here it strictly says that to find the HCF, you have to use the prime factorization method. But for the LCM, nothing has been mentioned, so you can use either the prime factorization method, or you can use the formula which is in the which has been introduced in the real number topic number 2, that is the HCF times LCM is equals to A times B. So first let's find out the HCF. So the numbers are 96 and 404. So I have to think of the common factors, so definitely starts with the 2. So 2 times 48, 2 times 202. Again, I'm gonna have the starts with the 2. So 2 times 24 and 2 times 101. Since 24 and 101 do not have common factors, so our HCF of 96 and 404 is 2 times 2, which is 4. Now for the LCM, I have to proceed further. So concentrating on the first number 24, so 2 times 12, so 101 will be as it is. Again, 2 times 6, 101, copied it down. 2 times 3, 101, copied down. 3 times 1, 101, copied down. And 101, 1 comma 1. Now, my LCM is 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, 16 times 2, 32, 32 times 3 is 96, 96 times 101 is 9696. So the LCM I have got using the prime factorization method is 9696. Now let's see how much LCM I'm going to get using the formula HCF times LCM equals A times B. So the HCF which I have just found by prime factorization method, replace it over here. LCM we do not know yet, and A and B are the given two numbers, which is 96 and 404. So since I have to find the LCM, I'll just have to keep it on one side. On the other side, I already have 96 and 404. But this 4, if you take it to the other side, it will go down in the denominator. So 4 will be down. And 4 and 401 are the multiples. So therefore, I have 96 times 101, which is 9696. So hence my LCMs are both are correct. So you can either use this formula, or you can use the prime factorization method. Doesn't matter, since in the questions nothing has been mentioned. Moving forward to the next example number 4, we have find the HCF and LCM of 6, 72 and 120 using the prime factorization method. So far we have came across only 2 numbers, right? But this time we have 3 numbers. So the method will be exactly same how you have done the prime factorizations for 2 numbers. So let's see how we are going to do for 3 numbers. So the numbers are 6, 72 and 120. So again, to find the HCF, the method is same. So we need the common factors of all the three numbers, and that is 2. So 2 times 3 is 6. 2 times 36 is 72. 2 times 60 is 12. So again, as you see, this next number is 3, 36, and 60. All these three numbers are multiple of the prime number 3. So I will have to take the 3. So 3 times 1 is 3. 3 times 12 is 36. 3 times 20 is 60. So next, the first number has been converted into 1, which means our HCF is 2 times 3, and hence HCF of 6, 72, 120 is equals to 6. Now next number, 12 and 20, if you look at, both are even numbers. So I'm going to go with the prime factor 2. So 1, we will just copy it down. So 2 times 6 is 12, 2 times 10 is 20. Again with the 2, 1 copied it down, 2 times 3 is 6, 2 times 5 is 10. Then it will be 3, 3 times 1, 5, take it down. So at the end we have 5. So our LCM of 6, 72, 120 is 2 times 3 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 3 is 72, 72 times 5 is 360. So HCF and LCMs are 6 and 360. Moving forward to the next example. So next example, we are given root of 3 and we have to prove that this is irrationals. So to prove this, we have to assume that root of 3 is a rational number. Root of 3 is rational number. So if root of 3 is rational number, what will happen is that root of 3 can be written as a by b form, where a and b are integers, and not just that, they are co-prime as well. Okay, next what I'm gonna do is taking the cross multiplications. It will be a equals to b into root 3, and squaring both sides, I'm going to get a square. This will be b squared into 3, so which is actually a square. I can rewrite this as this, and if I take the 3 to the other side, this will become a square by 3 is equals to b square. So what we know that from a non-theorem, so state the theorem. So that is, if p is a prime number and if p divides a square, then p divides a also, where a is an integer. Okay, so from this non-theorems, we will conclude that since 3 divides a square, it must also implies that 3 should divide a also. Next is you have to let a equals to 3c, where c is an integer, and squaring both sides, it will be a square 3c whole square, and replacing the a square with 3b square, it will be 3b square equals to 3 square is 9, with the c square, 3 and 9, you can cancel it out. So I am left with b square by 3 equals to c square. So here also again it implies that 3 divides b square, so it should also implies 3 must divides b, and hence a and b has a common factor as number 3, and this contradicts, right? This contradicts our assumption. So what was our assumption in the beginning? So this contradicts our assumption that root of 3 is rational number. Hence, if root of 3 as a rational number is a contradiction, then root of 3 has to be the opposite of rational number, which is irrational. All right. So moving forward to the next example. So next example, again, you have to prove this 5 minus root 3 as irrational. So this kind of equations will be a little bit easier or a little bit less answers than the previous ones. As you can see in the previous ones, it covered up all my sheet, but in the next you will see that answer is little bit lesser than the previous one. So let's prove this one as well. Oh, I'm sorry, so it says show that, so therefore you just need to show it. So to show that 5 minus root 3 is irrational, so what we are going to do is, let again 5 minus root 3 is rational. That is the case. Again, by definition, it will be in the form of a by b, where a and b are integers and a and b are co-prime as well. Okay, so simplifying this, I am going to separate the 5 and the root. Okay, so this root I am going to keep it on one side and this 5 a by b all to the other side. So this will become, since I have a negative root 3, if I take it to other side, what will happen is 5 will be as it is. A by b, I will take it to this side. So a by b sign is positive, so this will be, sign will get changed and equals to root 3. I am going to keep it on the right hand side, so sign will change, the negative sign will convert to positive, so this will be root of 3. Now if you look at here, what happened is 5 minus a by b, so 5 is, what is 5? So 5 is actually irrational numbers, right? And a by b is itself a rational number, so rational number minus rational number is always a rational number, whereas root of 3 is irrational number. So what it indicates is that here LHS is equals to rational number, whereas our RHS has a square root which is irrational. So we know that rational and irrational are completely different numbers, but in this particular equations they have written an equality, right? You can see an equality here, so this indicates that LHS is not equals to RHS. So LHS and RHS are not equals. Okay, so LHS and RHS are not equals, but over here it says they are equals, so therefore this contradictions, so we have a contradiction arising here. Why? Because in the previous step it says rational and irrational are equal, but here we are stating that no, they are not equals. So this contradiction arises due to our incorrect assumption, and thus 5 minus root of 3 is irrational. So as you can see, this example 6 is much easier than example number 5. Moving forward to the next and the last example. So again here 3 root 2, you have to show it as irrationals. So let's start. So let 3 root 2 be rational. Then 3 root 2 can be expressed as a by b, where a and b are integers and a and b are co-prime as well. Next is I'm going to replace the irrational and the rational separately. So already I have a root of 2 on the left hand side. I just need to take this 3 to the other side. So root of 2 equals to a by b is already on the right hand side. So if I put the 3 to the other side, this will definitely go down in the denominator. So that will be b times 3. So which is root 2 is equals to a by 3b. So again, the same concept, LHS. Now this time LHS is irrational, so please keep it in mind that you have to figure out where is the irrationals, whether it's on the left or the right. Okay, so it need not has to be that always the left hand side will be rationals and right hand side will be irrational. So you have to make out the LHS according to the equations which you have got it. So for the RHS we have only rationals, and thus LHS is not equals to RHS. Now the same thing, this contradicts. So this symbol is a contradict symbol. So this contradicts our assumption. Hence 3 root 2 is irrationals. So with this, we are done with the full complete examples of the NCERT textbook under the chapter number 1. So the next video I will be uploading regarding the exercises of the chapter number 1, and hopefully you will share and like the videos and subscribe to my channel, and thank you so much.